All right, it's 11:15. I think we'll get started. So this is the day that we review. I will review anything that you ask me. I have a couple things to say first, but you can get your questions ready. Of course, there's going to be extra office hours tomorrow. You can always make an appointment with me, but exam day is Friday. And so unless I hear from you before Friday, I expect everyone to take the exam on time. Unless you have an emergency on Friday, just send me an email. We'll figure it out. But, make sure that you're ready to rock. Okay, so I want to make sure that everyone understands how to polymerize dienes. And so dienes are a special class of monomers that we just introduced last time. And what's the degree of functionality of a diene? Is it? I hear 4. Is the degree of functionality 4 in these polymers? All these polymers are linear polymers. So these are all linear polymers, which means DF equals 2. So how does the DF equal 2 when you all see 2 double bonds in dienes, right? So here, what's this monomer called? Need to know this. Butadiene, 4 carbons is but, and it's a diene. And so notice that these double bonds are in conjugation. What if I have something like this? Oops, let me put an oxygen in the right place. There we go. Get my chemical structures okay. What's the DF of this monomer? 4. It's not a trick question. So why is the DF of butadiene 2 and the DF of this diacrylate 4? Because these double bonds don't communicate with one another. They are separate. There's plenty of carbons that are unconjugated between those. And you know that we have DF equals 2 for that. DF equals 2 for that side. So DF equals 4. And this gives a branched polymer or a cross-linked polymer. And so by the modes of diene addition, and you should commit this slide to memory, we're only making 2 connections to the polymer chain. So whether we have 1,2 addition, 3,4 addition, if we have an asymmetric diene, or cis 1,4 or trans 1,4, there's only 2 connections. And DF, an easy way to think about DF is, well, you look at the double bonds and say, okay, I have a DF of 2 for every double bond. But degree of functionality really means how many connections you're making to growing polymer chains. And in all of these examples, the number of connections that you're making to the other polymer chains is 2. So the DF is 2. And so that's really important, especially when you do cis 1,4 and trans 1,4 addition, where you move that double bond to the center. So notice that we start with 2 double bonds in the monomer, and in all examples, we have a double bond left over, right? And so we've only effectively used 1 double bond to connect to the polymer chain. That gives a DF of 2 for dienes. So the only thing you have to recognize, is this a diene? Do I have this situation or do I have this situation? Is you need to have some sort of double bonds, carbon-carbon double bonds in conjugation. And the only way in this class that we're going to learn how to do these diene polymerizations is either 1,3-butadiene or something like this, isoprene, but every diene structure in this class is going to be something like this. So it's going to have a butadiene framework and maybe one substituent on it. Yes.
So it's like, the two double bonds are cis to each other. We have to expect that as well.
Two double bonds are cis to each other.
Like that. For three, when they're switched, so it would be in parallel with the line two. Would that be?
Oh yeah. I mean, this monomer, of course, you have free rotation when it's a small molecule, and so yeah, that's how you get cis and trans isomers, right? So in one conformation you get the trans isomer, in the other conformation you get the cis isomer. Yeah, but all of these, for all dienes, you will have all of these types of addition, and so you need to memorize 1, 2, 3, 4, cis 1, 4, trans 1, 4. So all of those things you have to remember for these dienes. Now, the question is, what's the difference between 1, 2 addition and 3, 4 addition of butadiene? So if you have butadiene, what if you have 1, 2 addition versus 3, 4 addition of butadiene? What's the difference between those two polymers if I just have butadiene? It's the exact same, right? So there's only 1, 2 addition of butadiene. There is no such thing as 3, 4 because you always number the molecule with the lowest number substituent. So there is no 3, 4, but there is 1, 4 cis and 1, 4 trans addition of polybutadiene because those are different structures. So remember, when you do have a substituent like this R group right here, you will have 1, 2, and 3, 4 addition because you notice these chemical structures now are different. You have to look very closely, you have to count, you have to figure out where all the bonds are going. And so when you have this R group, that's always going to be on the number 2 carbon due to the rules of naming organic molecules. Remember, 1, 2 addition, you put the substituent connected right to the backbone, and 3, 4 addition, this is a pendant vinyl group. So that's a little tricky. That's new. You'll have to study that type of chemistry and figure out how to delocalize these bonds in terms of where you push the electrons and how you get the different structures. Any questions or comments on that? Yes.
So the double bonds that are left over from the 1, 2, and 3, 4 additions for the isoprene, can they go on and further polymerize as well?
By other mechanisms, it turns out. Yeah. So because these double bonds, either this internal double bond or this double bond right here doesn't have some of the same delocalization as styrene has or acrylates have, you can do chemistry on those, but not using this method. So they will stay pendant. And so you'll learn about that other types of chemistry in your advanced polymer classes. But for this class, this is as far as dienes go. Yes?
Where does the MATSE 1, 4 and trans 1, 4 addition came from? Do you understand that 1, 2, 3, 4 go through the 1, 2, 3, 4?
Yes. Yep. So cis means the same side. And so 1 and 4 are on the cis conformation or the same side of the double bond, just like you learned in organic chemistry. Trans means opposite, right? And so carbon 1 and carbon 4 are on opposite conformations, or if you look at the Newman projection, they're in the trans configuration. And so that we call that trans, because, or we call that trans 1,4 addition, because we can't rotate around that double bond, right? So that is locked in there. Yeah. Does that make sense?
Yeah, so it's based on what it looks like at the end.
Yes, absolutely. I mean, you can have cis and trans conformation of the diene, but it rotates. So that Newman projection you did when you did trans, gauche, etc. You know, this butadiene is rotating, and then when it's locked into a polymer, then the conformation is locked in. So you can't take cis 1,4 addition polybutadiene and turn it into trans 1,4 addition because you can't rotate it anymore. It's stuck. Does that make sense?
Yeah.
And so they're different chemical isomers. Good. Any other questions on dienes? All right. So my question for you, you can get out your clickers. So I'd like to see who's here. It's okay to take them out right when you come into class. All right. So we have trans, cis, and vinyl or 1,2 addition polybutadiene. So this is vinyl or 1,2. This is cis. This is trans. And the question is, which one is more crystalline? So we talked about this last time. Well, we talked about this way up here. Which one is more crystalline in terms of tacticity? And so we indicated that regularity of packing was a good thing, and thinking about how this might pack into a crystal. And so the question is, looking at these structures, and this is exactly sort of how they look like in 3 dimensions, if you can imagine that, which one is the most crystalline, or which one will pack the best based on just your visualization of what these things look like? I know we've got at least 50 people out there, so that's the number I'm looking for. Oh, maybe we don't have 50 people. Okay, last chance to sign in. We're close. So trans 1,4 polybutadiene is most regular, easiest packing, most crystalline. So you can say, well, you know, cis 1,4 looks pretty regular as well, and it's hard to argue with that, but that kink in the chain. So it's a lot easier to pack together trans 1,4 polybutadiene that looks like a pretty straight chain, just a zigzag. You know, it's easy to pack uncooked spaghetti, but it's a little bit harder to pack something that has a kink in it, because remember, it's got lots of kinks in it, and so you need to line those up. And so any cis conformation combats crystallinity, and of course this has a pendant group, so that's not going to be good. And so trying to decide between cis and trans can be difficult, but look for the most linear, most regular chain. Yes.
So you just kind of answered my question. So trans is not always going to be the most crystalline. So, but in how would you go about ranking, like, you know, personality of, or, you know, all of these, given that it's just a question?
Trans is going to be the most crystalline. Yeah. Because cis will always have this kink in it, right? I mean, I guess you could try and invent a structure where the cis, because of substituents on there, gets the right packing, but that's really hard to visualize. So in questions like this, where we're just dealing with polybutadiene, because we don't have any substituents on it other than the carbon-carbon backbone and hydrogen, it's always going to be trans, because that sort of extended zigzag is easier to pack than something that has these little U shapes in it, like the cis. So you want to be able to connect the regularity of the chain, the regularity of the stereochemistry, or the regularity of the shape with some sort of property that I asked you about. Yes. What does what say? Oh, most regular, easiest packing, most crystalline is the trans. Other questions, comments? All right, let us go to the review slides. So this is note set 17, and first I'll just say that we have extended office hours. I've had some good office hours chat, so you can ask me any questions you want on PLAs, on homework, on the practice exam. We can solve problems. We can talk through that. That's no problem. And so we have plenty of office hours tomorrow, no office hours today. Unless you email me and make an appointment, I'm happy to do other times, but you have to give me some warning because sometimes I'm not available right then. And email me through Canvas. You send me an email to my regular email, there's no guarantee I'm going to see it because I get lots of those. I get fewer Canvas emails, so I can really focus on those. So tomorrow 1 to 3 and 7 to 8. No questions on Friday unless there's a mega problem. If 20 of you are having an issue on Friday, that's a Canvas problem. If one of you are having an issue on Friday, I'll try and coach you through it, but that might be an individual issue. All right, so here's all the details, exactly the same as last time. Remember, use Firefox or Chrome, not Safari. I didn't hear about people having problems loading pictures, although Canvas did go down last exam, but we seem to get through it. That's nice. But make sure you refresh. You're not penalized for that, so you can load the pictures. Let's see. Okay, exam topics. So this is exam is really going to focus on chain growth. And so you need to know those free radical mechanisms: initiation, propagation, termination, chain transfer. You want to know the same thing for cationic. You want to know the same thing for anionic. You want to know the details of why cationic terminates differently than free radical. You want to know about living anionic polymerization and how that works. And so make sure you really focus on chain growth. However, you can't forget things like M0. You can't forget things like molecular weight, all sorts of stuff like that. So don't forget some of the basics, but there's probably not going to be like a Carruthers equation problem on this exam because we covered that last time. Yes. Yeah, so anionic polymerization without the living in front of it follows all the same rules as free radical and cationic polymerization in terms of initiator, chain transfer, all of those things. Remember, living anionic polymerization has different rules in terms of how we calculate the molecular weight and how we think about the degree of polymerization. So let me find living anionic here. Well, it's the fundamental equations that we use to describe. Where is it? Come on. Well, let's start here. So it's for living anionic polymerization, we've got an expression for the dispersity, right, in terms of the X bar N. And then we also have, oh man, I can't even find it now. Maybe it's in the previous one. Bear with me. Here we go. Fine, sorry about that. So free radical, cationic, anionic, it's the usual story in terms of all the rate constants, our fundamental equations for X bar N 0 and X bar N. If I say living, or if I say that we have an electron transfer initiated polymerization with sodium naphthalide, that's a key initiator for living. We describe the rate of polymerization of a living polymerization using this equation and the degree of polymerization using this equation, where we have now the molecular weight as a function of conversion, and that's where we get this linear plot. So the linear relationship between X bar N and conversion is only for living. So there has to be some hint in the problem that tells you it's a living polymerization. Otherwise, it's just your garden variety anionic chain growth polymerization. Yes.
So for living anionic radicalization, we'll hit
Hold on. For what?
living anionic radicalization.
There is no such thing as living. Yeah, living anionic polymerization. You got it. Go ahead.
How will will K always equal to?
What will K be equal to for living anionic polymerization? K equals 2 for electron transfer initiation. That's as far as we know in this class. Now, there's other types of initiation to get living polymerizations. We just don't study them in this class. So it's pretty much K is going to be 2 no matter what. And if you don't have any information on K, you just say, I'm assuming K equals 2 because that's how we've done all these problems. Yes. I might give you the molecular, I might give you X bar N, right? I might give you, some other variables. And so again, being able to solve the equations forward and backward, right? Identify what the variables are, figure out what you know, figure out what equation gets you to where you want to be. And you might have to solve for M0. So you had to solve for monomer concentration in one of the practice exam problems because I gave you X bar N. And so being able to identify what's going on, because I could give you a huge list of equations and say X bar N equals monomer concentration equals initiator concentration equals, but there's no use to that because it's just rearranging the same equation over and over. And then you have a lot of different equations. And so we tend to stick with the fundamental equations, and then through the identification of the problem and the variables, you're able to pick out what you need to solve for. Yeah, so that's a really important lesson. It's not always plug and chug for X bar N. It's figure out what I need to solve for and figure out which equation I need to use for that. So my advice is that there are some key hints for living anionic polymerization, and the key hint is sodium naphthalide or electron transfer initiation, or I just tell you it's living, right? Do living polymerizations have a termination step? No, that's why we call them living. Or if I give you this plot, if I say that X bar N is a linear function of conversion, then you know exactly what type of polymerization is it's living versus step growth or chain growth. Is that good? I forgot who asked the original question, but does that cover it? Yeah, all right. Let's see, other topics. Make sure you know some common chemical structures. Since we're dealing with chain growth polymerization, you shouldn't forget amides, esters, you shouldn't forget that step growth chemistry, have that in your memory bank, maybe just review it in case ester pops up on the exam, you know what it is. But it's really thinking about vinyl monomers that look like this. And of course, dienes, which are special. Don't forget about those and know how to deal with dienes, because I guarantee you I will ask 1 or 2 questions on dienes on the exam. And I'll ask you 1 or 2 questions on stereochemistry on the exam as well. Mayo-Walling equation, you had a homework problem on that, and that deals with all sorts of chain transfers. So before class, we were discussing what happens with the degree of polymerization when you have chain transfer. And the rule is, when you have chain transfer to polymer, what happens to the degree of polymerization? Nothing. So in all cases, radical, anionic, cationic, when you have chain transfer to polymer, nothing happens with X bar N. When you have chain transfer to anything else, solvent, chain transfer agent, monomer, initiator, what happens to the X bar N of that polymer system? It decreases, right? So those are the only 2 things you need to know. There's no special cases for the different types of polymerizations. Now, we did study 2 different types of chain transfer to polymer cases for free radical polymerization, right? And so in free radical polymerization, how can we get chain transfer to polymer? What are the two modes? Intermolecular chain transfer and intramolecular chain transfer. And so make sure that you know what happens to those two modes and how you identify them. So when you have intermolecular chain transfer to polymer and free radical polymerization, you get what types of polymers result from intermolecular chain transfer? Long branches, right? That is the signature of intermolecular chain transfer. And for intramolecular chain transfer, what type of things happen to the polymer chain? Short chain branches, right? And so if you have intramolecular chain transfer for cationic polymerization, you get the same sort of thing. Even though we didn't write out those mechanisms, just remember intermolecular chain transfer versus intramolecular chain transfer. Now, you're not going to have to write tens of chemical mechanisms on the exam, right? Because it will be multiple choice. You'll have to identify what's going on. Perhaps you'll have to write a little chemistry on the written part, but it's not going to be like one of the homework problems where you had, you know, a bunch of different things to write. I'm not looking for you to list off all the different mechanisms of free radical polymerization, but I will ask you targeted questions about what happens in disproportionation versus what happens in combination versus what are the end groups. You've had homework problems on that. And so you will have to write some chemistry, but it won't just be a big laundry list. It'll be a targeted question. Let's see, what else? Principle of equal reactivity, that is still in play. And so what does the principle of equal reactivity say again? What does that mean? Yes. That's right. Growing chain ends are the same reactivity no matter what the molecular weight is. And so that is still in play for here. Let's see, you need to know what the active centers look like. And let me move this thing here. And initiation or initiators for each. And so it will be obvious if it's a free radical initiator, you know a couple of what those look like. The cationic and anionic initiators are a little bit more opaque, but I'll make sure that there are hints in the problem that you know whether it's free radical, anionic, cationic, or living. Let's see, dienes. All right, we have everything else. Any questions on this nomenclature or these vocab words? We have a bunch of questions. We're gonna sort of do some short answer stuff to review, but any questions on stuff on this slide, words that you have no idea what's going on, concepts where you're not sure? I'm happy to cover any open questions you have. Yes?
Can we talk about what thermostats are again?
Sure. So let's start off. What's the complementary word to thermoset? So we have thermosets and thermoplastics, right? Those two words go together. And the way that I remember it is thermoplastic means heat and deformation. And so thermoplastics mean that you can deform polymers with heat, or you can reprocess them or shape them with heat. Thermosets means that they are set and you can't process them with heat. So thermo is heat, set means it's all set up. And so the only way that we get a thermoset is if we have a cross-linked polymer, because those covalent cross-links lock in all the chains and it's set. Thermoplastics have to be linear or branched. So even a branched polymer can be a thermoplastic because those chains can slide past one another. Because anytime we deform a polymer, there's chains sliding past one another to change the shape of that polymer. So thermosets can't be reprocessed with heat. That's the basic idea. And then you need to remember things like TG, TM, what are those? How does that matter? You know, what's for the amorphous phase, which is the TG, the glass to rubber transition. what happens in semicrystalline polymers. That's a TM when you melt the crystal. So you want to just remember some of those concepts and have them at the ready, just like we talked about in terms of when we're talking about tacticity. You know, I could ask you questions directly about tacticity, but I asked you a question about, whoops. Come on. No, it was down here. I asked you a question about crystallinity, and this is not tacticity, this is dyeing addition, but I wanted you to connect that concept to what we were talking about with dying. So, you know, that's why you should remember some of the basics like TG, TM, what a thermoset is, what a thermoplastic is. Good question. Other questions? All right, let's see, what do I have here? Yep, focus on chain growth, you know that. Okay, we talked about that. We talked about dyeing addition. All right, so you can get out your clickers, and this is just a review. This is the easiest dyeing addition problem. So first, you have to recognize that this is a dyeing. And then you have to know, I'm likely not gonna number the carbons for you. You have to know how to number this thing. And I think we asked this last time. And so the question is now, what does the 3,4 addition product look like? And the numbers tell you where the polymer chains are. And so the question is, if I put a polymer chain through here, how do I find the right structure, right? So let's see, there's no double bond to the polymer chain. That's out. This is out because this is 1,4 addition. I need a pendant double bond somewhere. And so the question is, how do I tell the difference between those two? Those two look similar to me. If I'm going fast and, you know, I don't have, you know, great resolution in Canvas on the diagram, how do I tell the difference between those two structures? What's the key? You look at this 3 carbon right here, and I've got 1 bond to carbon 2, and then another step to carbon 1. So it can't be C, it has to be A. I have a single bond to carbon number 2, and then I've got carbon number 1 right here, because I did 3, 4 addition. Make sure you know how to do that, because this should be a relatively simple dyeing problem, but it can get complicated because there's generally in a multiple choice exam, right? There's 2 answers that are kind of close. One is right and one is wrong for a very specific reason. And I think you experienced that on the last exam too. Questions? All right. We already talked about that. All right. Okay. So this next series of questions, I don't have clickers yet, but this series of questions will prompt us talking about some things, and we can go through them together and then look at the answers. So compare and contrast radical and ionic polymerizations. And when we say ionic, it could be cationic or anionic or living, right? So all chain polymerizations require initiation, but the initiator must usually be activated with light or heat for what type of polymerization? Radical, right? Good. Let me do that in red. So we talked about radical initiation by light, like benzophenone and things like that. AIBN is a thermal sensitive initiator. So it doesn't mean that there aren't other initiators that we can use for ionic polymerizations that you can initiate with heat or light. That's an active area of research. But we're trying to find the most reasonable answer. Well, the initiator is already completely activated at the start of the reaction, usually for ionic, because especially in cationic polymerization, it was all ready to go. It was an acid or something like that. Great. Benzoyl peroxide would be a good blank initiator for what type of polymerization? Radical. That's one that you should know for sure. What's the other radical initiator that we talked about a lot? AIBN, right? You don't necessarily have to memorize the structure of benzoyl peroxide or the structure of AIBN. I'm not going to test you that deeply, but when you see it, you should know what it is. And what's the dead giveaway for why we know that this is a radical initiator? It's got this peroxide bond, which is an oxygen bonded to oxygen, and peroxides make radicals. That's what they do. Same with AIBN, it liberates nitrogen and makes radicals. So if I show you a picture of a radical initiator, you should be able to tell me how it makes radicals. All right, sodium naphthalide, a very special initiator. It's a key word, it's nice and long, would be a good initiator for what type of polymerization? Anionic, and especially what type of anionic? Living. So we didn't study living cationic polymerization. There is such a thing, but we didn't talk about it. So we focused on living anionic polymerization, and this is a key hint that it's going to be living anionic. Good. And I think we got them all right. Good. I hope so. Great. Okay. So comparing radical and ionic polymerizations, and we're talking propagation here, okay, thinking about propagation of the growing chain end. All reactions tend to propagate in a what to what orientation? Head to tail, not tail to head. Why isn't it tail to head? They're just the opposite. Why doesn't it go tail to head? Because the head is what can support the radical, right? And so remember, the head is the most substituted carbon. This is the tail, which is the least substituted carbon. And so if we think about the active center, say in a growing chain of styrene, this radical can be delocalized by resonance, right? It's the most substituted carbon, it's the most stable radical, and the growing chain end is most substituted carbon. Great. Why does it add to the tail? Why don't I just get head-to-head addition? Sterics, right? So even when you have halides, even though halides destabilize radicals, because of sterics, you always have addition to the tail because of sterics and because it makes the most stable radical again, right? So it's always sterics, whether it's anionic, cationic, or radical polymerization, it's always head to tail addition. So growing chain end is on the head and it adds to the tail of the next monomer. That's what head to tail addition is all about. You should know when to recognize tail to tail defects or tail to tail connections and head to head connections. So you should have some of that knowledge in your memory bank, but this is the important piece of information when we talk about propagation. Any questions on that or comments or things that are unclear? All right. Great. So, you know, I can ask you short answer questions like this, or I could label a monomer, you know, with different head to tail and say which is correct, you know, which has a head and tail label correctly. So make sure you know the concept, and then you're able to look at the monomer and identify what's the head and tail. So make sure you're able to do this type of problem both ways. All right, here's a clicker question. Consider the second step of initiation. Okay, so I've made my initiator and I have that initiator fragment. And the second step of initiation is what? That initiator fragment does what next? Adds the first monomer, right? So this is a step before propagation where an initiator fragment grabs the first monomer, and that's called the second step of initiation. All right, cationic polymerization of styrene. So I tell you the mechanism, I tell you the monomer. You should know what styrene is. I might give it to you on the exam, but I might not. We've talked a lot about styrene, so this should be in your memory bank. Where the initiator is R. So the first step of cationic initiation is just getting this R plus, right? And so step 2 is R plus is going to react with our styrene. And so the question is, what is the product of this reaction? What does it look like at the end of step 2? So you can ring in. I think we've got 49 people today. So the question is, what kind of bond does this make? And where does the growing active center wind up? Because we need that, we're doing cationic polymerization, right? So that cation has to live somewhere, and we need to get the right type of bond. And so if we think about 2 electrons coming over and making a bond, all we have to do is say, okay, I've got R, I make a covalent bond to 1 carbon on the styrene. I've got another carbon of the styrene. Oh. One carbon right here, 1 carbon right there. I've got my styrene ring. And I'm going to have my cationic center here. So I think that's the right reaction that I wrote on my scratch paper. Now I just need to go and figure out which letter that is, right? So let's see. My cation is living next to the styrene. Okay. I've got an R out here by itself, but I don't have this cationic center out by itself there. I don't have the cationic center on the tail of the styrene. That's out. This thing looks a little bit funny. I'm not sure what's going on with D. And so it turns out that this structure is exactly the same as this structure. So no matter how I draw it, I can identify that the growing chain end is on the head, and the initiator attacked the tail of styrene, because remember, this is the head, this is the tail, and it looks like that. So B is the correct answer. So that's tricky, right? I need to figure out how to make that covalent bond. I needed to remember what step 2 of cationic initiation was. And I needed to make sure that I have the growing chain end in the right place and that this bond looks good to the tail. Questions or comments on that? So it might be the same thing for anionic. It might be the same thing for radical. It might be talking about, here's a propagating chain end, and I'm going to add the styrene. This question could be asked about propagation. What does the next monomer unit look like? And so you'll have to be able to make the right connection and then show me where the growing chain end is. All right, next one. This is a little bit harder. Which correctly depicts the most likely arrow pushing mechanism for the propagation of the polymerization of this monomer? Okay, this monomer, it's just got 1 carbon-carbon double bond in it, so we can treat it same as all our other vinyl monomers. I suggest you identify the head and tail first. So I'm going to polymerize through the double bond. What is this, the head or the tail, this carbon? That's the tail, which means the head is the other part. Okay. And so as I propagate that, or as I arrow push that, I know that my active center is going to want to end up on the head, right? And my growing chain end is going to want to attack the tail. So I just have to figure out first which growing chain end is accurate. Notice that these 2 sets of growing chain ends are different, and which addition to the monomer is accurate. Am I adding to the tail or am I adding to the head? This is as hard as it gets because I give you 2 options for what the growing chain end looks like. I give you 2 ways to add the monomer, I made it a little bit easier on you because hopefully you identify that I can only add this monomer in one way. There aren't any functional groups, not any funny business going on. So the question is, what's the right growing chain end and what's the right way to add the monomer? And we could just think about this in terms of how do we get a polymer chain where we get the growing chain end on the head carbon. So we know the polymer chain goes through that double bond. We can put the growing chain end on that head carbon, and then we've just got this substituent hanging out there. So the right growing chain end is either A or B, right? Because I just have this substituent hanging out. I can't have the growing chain end down there. There's no way to put the radical down to this carbon down here. And so is A or B correct? We know that free radical addition always precedes what to what? Head to tail. And so does A or B depict head to tail addition? B, that's right. So this is the tail, that's the head, and that's the correct mechanism. And I think that is what I have. There we go. Head to tail. So that's hard because you do need to get the active center correct and you do need to get head to tail correct. Yes. C or D, these have wrong growing chain end. So these both have, if you count the carbons here, 1, 2, 3, 4, these both have the growing chain end on carbon number 3. And we never studied an example where the growing chain end moves away from the head carbon, right? So this is tail carbon, this is the head carbon. The growing chain end is always sitting on the head carbon. So that is tricky, right? You're like, you know, okay, I want head to tail addition. I'm going to pick C. And it's not wrong because of head to tail addition. It's wrong because the growing chain end is not on the head. Does anyone not get that? This is a key problem. I promise you I will ask you something like this one or the previous one about how to move that growing chain end. And you're going to have a few possibilities. You should be able to write these out because I could ask you in the written part. But being able to decipher this in multiple choice is important. Yes.
So why is the case in C, like where that the growing chain end, why is that more substituted than the one in A? Like why is that the head? I guess. Is that like,
Oh, well, this is a C is a false head. That's not a real structure. So C doesn't exist. It's wrong because that's not possible.
oh, okay.
Yeah.
Okay. Cool.
Because the head, the growing chain end is wrong. It's just straight up wrong, doesn't exist. You know, you notice both A and B have the right growing chain ends. So that's good. That's good because growing chain end is sitting on the head. That's fine. It's just that the addition of the monomer is wrong in A.
Okay, I see.
Yeah. So it's tricky. You know, where's the head? Where's the tail? Where does that active chain end go? That's all important. Other questions, comments? Yes.
So in this case, C and D are not possible and A is possible but less likely.
That is correct. Yeah. Which depicts the most likely arrow pushing mechanism. So A is a very, very minor product. Yes.
So is A
A is head to head. Yeah. So A is head to head, which is way more or less likely. And so again, the magic with the multiple choice exam is pick the best answer. And that's usually most likely, most common mechanism. Any final questions? Okay, take advantage of office hours, take advantage of an appointment if you need it, and don't forget to take the exam on Friday in a good place, be ready for it, and I will see you in person on Monday. Remember, there's no in-person class on Friday. There's no homework this week. It's all about the exam on Friday. Thank you very much.